In this video, we're going to talk about rates of change. As we've seen before, the derivative can be used to find the slope of a tangent line or an entire function. But a derivative can also be used to find the rate of change of one variable in respect to another. For example, like dy over dx, which represents the derivative of y in respect to x. A common use for rate of change is to describe the motion of an object moving in a straight line. So a car moving horizontally, or a ball that's launched in the air moving vertically. And often those are graphed as either horizontal or vertical lines to show a starting point and an ending point. And if the graph moves to the right or up, that's moving in a positive direction, and if it goes down or to the left, it's moving in a negative direction. And what we can do with rate of change is talk about an object's position over time and its velocity over time. Now, in calculus terms, let's say I have an object and it starts somewhere, so the origin, and it's going to move its position over time. I can write a function for how that object moves in terms of time, and I'm going to call that function s, let's say. So it gives the position relative to the origin, or where it starts, of an object as a function of time t. That's called the position function. So if over a certain amount of time, so as time changes, we use delta t to represent that, the object is going to change its position. So we use delta s to represent the object's position change. So I represent it by this formula. And taking the position function over time and adding in the idea that rate equals distance over time, I can then find the average velocity. So that's a change in distance over change in time. So that is delta s over delta t. Let's take a look at this example. So let's say I drop a billiard ball from a height of 100 feet. The ball's height, s, at time t, is this position function here, where s is measured in feet and t is measured in seconds. And now I'm being asked to find the average velocity over 3 different time intervals. So I'll start with this first interval. So what it's asking me to find is the average velocity from 1 to 2 seconds inclusive. The first thing I do is plug in 1 for t and 2 for t and find those heights, and then I plug them into my average velocity change in s over change in t formula. So I'm going to do 2 minus 1 in each scenario, and I'm going to get negative 48 feet per second. Now let's work out these other two examples and see what we get. For B and for C, I employ the same methods that I used in part A, and I find in part B from time equals 1 to 1.5 seconds, the average velocity is negative 40 feet per second, and from 1 to 1.1 seconds, it's negative 33.6 feet per second. So because velocity is change in position over time and our results are all negative, that means that this billiard ball is traveling downward. We can actually take the idea of average velocity and apply it to something called instantaneous velocity. And that's just what it sounds like. It is the velocity of an object at a certain instant of time. So we take the position function where we have s is equal to s of t, where t equals time, for an object moving along a straight line. Then the velocity at time t, remember at that instant, is going to be this definition here. So you see that we've introduced the limit as delta t approaches 0. That means that the time between our intervals is nothing, so it's instantaneous. And we're going to use that same definition that we had before, and if you look, that's actually the derivative of our original s position function. And we can represent that position function for a free-falling object with no air resistance under the influence of gravity as this equation right here. We've got our old friend s of t, and we see t in that equation in 2 places, but we also have new variables here that we can plug in information in order to work with that position function. First being g, which represents acceleration due to gravity. Now if you're working in feet, you're going to plug in 32, and if you're working in meters, you're going to plug in 9.8. You have this v naught here, which is the initial velocity, and then you have this s naught, which is the initial height of the object. Now let's work through an example of this. So let's say at time 0, a diver jumps from a platform diving board that's 32 feet above the water. Now, because the initial velocity of the diver is 16 feet per second, the position of the diver is this S of t equation here, where S is measured in feet and t is measured in seconds. Let's find two things. Let's find when the diver hits the water and what the diver's velocity is at impact. So for part A, the diver is going to hit the water when S, or its position, equals 0. So I set this equation equal to 0. I'm going to factor, and I'm going to have two answers because it's a quadratic. One is positive and one is negative. Now t is in terms of seconds, and that's time. So I'm not going to use the negative one. I'm going to use the positive one. And that's going to be t equals 2 seconds. So that's when the diver hits the water. So for part B, what is the diver's velocity at impact? Remember, velocity is the derivative of this S of t function. So the derivative is going to be negative 32t plus 16. And that's where I plug in the answer from part A, t equals 2 seconds, right in here for t in our derivative of S of t. And I'm going to get the velocity at impact, the instantaneous velocity at 2 seconds, is negative 48 feet per second. And just like in our last example, if your velocity is negative, that means that the object, and the diver in our case, is moving downward. And that's going to do it for this video. Thanks for watching.